Hey everybody, I am beginning our last lecture. This is chapter 12, so it's the last chapter we cover in 111. There's no video lectures for 10 and 11 because they're sort of very quick, and we did them in class about a month ago now, 3 or 4 weeks ago. So those lecture notes are available for you. Hopefully you wrote some stuff down during class. All right, so I've updated this for the 2017 fall semester. Okay, so you can jot this stuff down if you didn't get it down in class. Okay. It's important to check your final exam schedule in advance. Don't wait till the week before. And if you have any conflicts, get it worked out by discussing with me and your other professor. Okay, so we learned in chapter 9 about the concept of converting between one substance and another one. This is called stoichiometry. All right, and so it's a fancy word that just means if I know the amount of one thing and I have a balanced reaction, I can figure out how much of any other thing is involved. So for example, this is citric acid. Okay, so citric acid. It's in a lot of food and beverages that you eat. Anything that tastes fruity most likely has citric acid in it. And it reacts with baking soda. Okay, the formal name of baking soda is actually sodium hydrogen carbonate. Okay, but we call that baking soda. It's the same thing that you use in, cooking and everything. So if I take one citric acid, this whole thing is one citric acid, and I react it with 3 molecules of baking soda, it's going to produce 3 CO2s, 3 waters, and 3 of this, which is sodium citrate. Okay, I just want to break this down a little bit more. When you look at these two things, you would anticipate, most likely, it's going to do a double displacement. Okay, because we have 2 compounds, right? So generally we said that if you have 2 compounds, it's most likely either double displacement or maybe a combination reaction. All right, so in a double displacement, the 2 reactants, basically the cations switch place. So what I mean by that, like if I wasn't given the products here, then what I would expect to happen, since I have 2 compounds, I'm going to assume it's a double displacement. So the cation is the first thing almost all the time, and so it's the positively charged particle. Hydrogen here has a +1, so that's the cation. The cation in this is sodium. Sodium has a +1 as well. It doesn't have to match the charge, that's just coincidence here. But in this case, the sodium and the hydrogen are the cations. So what's going to happen is that they're going to switch places. The sodium is going to connect up with the other part of the citric acid, everything except the hydrogen. So we're going to kick out the hydrogen, and the hydrogen's going to... So the sodium's going to pair up here, and the hydrogen's going to pair up with the negative part of baking soda. So what we would probably first predict is that you're going to get sodium with this thing. Now I know since there were 3 hydrogen here, that this entire piece here, this thing, it's a polyatomic called a citrate, is a -3. I used deduction to figure that out. The 3 hydrogens here give me that clue because each one of them is a +1. Okay, it's got to be balanced. So sodium is a +1 as well. That means I got to have 3 sodiums for this reaction to happen. And then the other thing that happened is that H is going to come over to here. All right, and so this HCO3, this thing, that wasn't a very good bracket, but you get the idea. This HCO3 must be a 1-, and I think it might be on the back of the periodic table too, because I have only 1 sodium, and that's a +1. So I can use the information, in the formulas to begin with to figure out what the products are going to be. All right, so if I take out the sodium because it went over to this part, and I put in a hydrogen instead, Well, we already have hydrogen written. It was HCO3 with a -1. So if I put in another hydrogen, it becomes H2CO3. This is still an acid, so it's aqueous. Now, that's the double replacement step. So we have replaced the cation the citrate connects up with the sodium, so we're replacing the hydrogen cation, and the hydrogen connects up with this hydrogen carbonate group. Now the thing about H2CO3 is it's unstable. It's wildly unstable. This is called carbonic acid, and every single time I do a reaction that makes carbonic acid, it has a second reaction that happens right away automatically. I don't have to do anything, it just happens. That carbonic acid is going to break up into water and CO2, which is gas, so it's going to bubble. We had a reaction like this as one of the examples in the homework last week, okay? And so the trick is that the first reaction is a double replacement, and the second reaction is a decomposition. Our overall reaction is going to be what I have left over after I add up both of these things. So our product, or reactants rather, are going to be citric acid and sodium carbonate. That's what we start with. The Na3C6H5O7 is still there. But this H2CO3 is gone, it decomposed, so that's gone. So that's not in my final reaction. Okay, but the H2O and the CO2 are going to be there. Now, we didn't quite finish this step up here in the blue. We figured out that we have to have 3 sodium with 1 citrate to make a compound, and 1 hydrogen with the HCO3 to make that a compound. Now the problem is that's not balanced because we had 3 hydrogen here. So if I only added 1 hydrogen to this, that means I got to put a 3 in front of here because otherwise it's not balanced. Okay, so if I have, and then I also need to have, if I do that, that means I have 3 HCO3s, and over here I've only got 1, so I'm going to put a 3 there as well. And that's where this 3 came from. Alright, so if I have 3 H2CO3s, that's going to carry on into the next reaction. So I've got 3 water and 3 CO2s. So I have to balance the first step of this reaction first, and then I can balance the second step. So it's easier to think of it as a 2-step process. The overall reaction from start to finish, so not counting the bits in the middle, the overall reaction is this one written out here. So the question is, how many molecules of citric acid are going to react with 9 molecules of baking soda? Well, this is a stoichiometry problem, just like we were practicing in class and the lecture notes. So 9 molecules of baking soda. And I want to get rid of that. So dimensional analysis says that if I want to convert something, I put the thing I'm getting rid of on the bottom. And the thing I want to get to, which it looks like is citric acid, on the top. Whoops, I drew too many H's. Okay, there we go. So it's H3C6H5O7. There we go. Now, to fill in the numbers, the relationship between how many baking soda and how many citric acid, it comes from the balanced reaction. So we look here, there's no number here, which means secretly there's a 1. So we have 1 citric acid for every 3 baking soda. So there's a 1-to-3 ratio, we would say. 1 citric acid for every 3 baking sodas. Now the baking soda's on the bottom because I want to be able to cancel this unit and get just the citric acid, which means what I'm going to put in my calculator, what I'm going to do mathematically, is this 9 divided by, because it's on the bottom. So that's going to equal 3 molecules of baking soda. I'm sorry, of citric acid, actually. Okay, so here's a tricky question. If I had 1 gram of citric acid, would it react exactly with 3 grams of the baking soda? And the answer to this question is, without a doubt, no. because grams are not equivalent ways of measuring things. If I get the formula weight, like we learned in the last section, last chapter, and I compare them, they're not going to be the same formula weight. So that means that the mass is going to contain a different number of molecules for each of these, right? The only way to compare two different substances is by figuring out the moles. So when I have a question that asks me to convert from one thing to another, I have to get into moles first. So first we got to get here. Sometimes it might be from atoms or molecules or maybe mass. Okay, so however it takes to get here. Once I'm in moles, then I can convert between moles of one substance and moles of any other substance. I'm just going to write moles of something else, right? Moles of other. The way to do this conversion is to use the reaction. Okay. So, a word about this figure. I cleaned up some of the typing in this version of it, but if this doesn't make sense to you, if it's not helping you to strategize, then you can try two things. One is to make a strategy map before you try to use this. All right, so we got to identify where am I to start with. All right, that's a unit thing. Look for the unit. And then you got to identify where are you trying to go. All right, so like in this problem here, we're going from molecules to other molecules. We can compare those directly. We can also compare moles. I could not compare mass because the mass of a material reflects a different number of particles than another one. So like our baking soda mass is bigger or smaller than our citric acid mass, which means you're going to have a different number of particles in each piece. Okay. So, this is a review from the last chapter, but if we have 0.42 moles of citric, and I need to know how many moles of baking soda are going to react, I want you to fill this in. Tell me what conversion factor to use and what the answer is. Okay. Here's another one to practice with, all right? So, pause the video and give it a shot, and then I'll give you the answer, and you can tell if you're doing these conversions correctly. Okay, so 1.4 moles of NaOH is our starting point. And I know that because it's the only number in the whole question. And I want to get to H2SO4. So it's always going to be dimensional analysis, the entire chapter. This one and chapter 9 are nothing but dimensional analysis. So I'm going to put a fraction and multiply it. I put the NaOH on the bottom so that it will cancel with the NaOH I'm starting with. And I put what I want on the top. And then I got to find some numbers to go with this. There apparently is 1 H2SO4 and 2 NaOH. So basically what I have to do is go 1.4 moles, NaOH cancels because they're on opposite sides, divided by 2. The 1 doesn't affect anything because multiplying or dividing by 1 doesn't change the number. So what I get is 0.7 moles of H2SO4. That's the answer to the question. It asks how many moles. So I'm going to guess A. A is the correct answer here. Okay, hopefully that's what you got. But if it wasn't, then you need to take a second and figure out what's different. What steps were you missing, or what did you do differently? All right, so now this question is asking for a mass if 1.26 moles of baking soda were used. Now, anytime we're going between mass, which is grams, and moles, or the other way, you could even go backwards. You can go moles to mass, of course. That is going to be the periodic table. That's where we use the grams per mole from the periodic table. Okay, so knowing that, we're going to start with 1.26 moles of the baking soda, and I'm very careful to always write which chemical I'm talking about, because we're going to transfer between one chemical and another, so it's important to keep it straight. I need to know how many grams for every mole there is. So this is the molecular weight calculation we've been doing. Na says 22.99, H is 1.01, C is 12.01, and there's 3 oxygens worth 16 each. So our total molecular weight is going to be 84.01 grams for every 1 mole. I knew to use this relationship because I was trying to go from moles to grams, so that's the only way to do it, is to figure out how many moles are in or grams are in a mole, rather. I put grams on top because that's what I'm trying to get to, and the moles will cancel this way, and so we times that by 1.26, and we get 105.853. I only have 3 sig figs, so I guess I'm going to just write 106 grams. Okay. All right, I would like you to tell me the answer to this question. It's probably multiple steps because we're starting in grams, and I can't compare 2 different substances in grams. I have to go through moles. So pause the video and go ahead and do this one. This one is graded. All right, so here's an important idea. I have an Xbox and I decide to hold a party, so 7 of my friends come over, but I only have 4 controllers. Obviously, this means 4 people get to play and 3 people have to wait. So the thing that limits the fun of the party, the thing limiting, is my controllers. My controllers are the thing I need more of in order for everybody to play. All right. This is similar in chemistry to the idea of limiting reagents. I have a limited amount of something, and something is going to be used up. And if it is used up, I can't continue to produce products. It's like if I have a bicycle factory, and I need 2 tires for each bike and 1 frame. Let's say for a second that I have, I don't know, 100 frames that are all made and ready to go. And I have 400 bike tires. The question is, how many bikes can I actually make with that? Well, we said that there's 400 tires total, and every bike needs 2 tires. So kind of in the same way we've been setting things up, the tires are going to cancel. We get 400 divided by 2, so you could make 200 bikes with that. On the other hand, based on the frames, you only need 1 frame for every bike. So I can make only 100 bikes. Both of these statements can't be true. I can't make 200 and 100, because if I make 100 bikes with the frames, I've used up all my frames. I don't have anything left to put the tires onto. So in reality, I can only make 100 bikes. I've run out of my limiting reagent, my frames in this case. So the same thing can happen in chemical reactions. So here's an example. If I have 10 moles of H2 and 7 moles of O2, which one do I run out of first? So that's the same thing as saying which one is limiting. Limiting, meaning I ran out of it. Okay, so to answer that question, we have to convert from one substance to the other. So 10 moles of H2 would be the same, it would react with exactly, let's see, there's 7 O2 for every 2 H2, so that's our ratio. So I'm going to put in 10 times 7, which is 70, and divide that by 2, so that's 35. We get 35 moles of water. Sorry, no, not water. I'm crazy. Just oxygen. So if I base it on hydrogen, it's going to produce 35 moles of O2, or react with 35 moles of O2. Then the question I ask myself is, do I have that much? And the answer, of course, is no, I don't. I only have 7 moles. So that means that I'm going to run out of oxygen way before I run out of hydrogen. Okay? So we have to use mole ratios. I can't compare just the numbers of moles. I have to think about the fact that I have 2 hydrogen for every 1 oxygen. That's an important thing. It doesn't matter which one you convert, by the way. I chose to pick H2 because it's the first one I wrote down, but I could pick O2 and figure out how much H2 it's going to react with, and it's equally valid to do either one.